continue with the component level review of the schematic. In the last video I discovered that the MOSFETs that I chose were all bought up from Mauser, so there was like 0 in stock and 30 weeks lead time. So I replaced them at first with a different MOSFET that had the Power Pack SO8L package, which is a little smaller package. But I ended up actually changing back to a different MOSFET, which I found here. So I should probably definitely use a TO package. But since this is a Rev A, I want to evaluate some of these MOSFETs. I'm not going to be using that many, and I have, let's hope that all of these, how many, like 2,000, 4,500, 5,000, around like 5,500, 5,738 MOSFETs are not going to be bought up, and that I can at least evaluate this MOSFET on a few Rev A boards. But I should probably just change to a TO package, because like there are millions of MOSFETs that fit into TO package, and that would be the most the safest bet when there are not many components that use this PowerPack 8x8 package yet, at least. So we'll see by the end of this design if everybody has bought the components that are seen in this video. But until then, I'm going to be using this one, which is 60 volts and 63 amps. Next, let's see. So we're going to move on with this list. Next, we've got all the resistors. So we're going to go over as many resistors as we can, and check, just make sure that the power of the resistor is, or the power dissipation of the resistor is sufficient, and that it has the right footprint as well. Now, there are many resistors that have the same resistance, so it's going to be a bit of I think what we should do is actually sort them out by sort of, let's see, I'm going to see if I can maybe print a list of unique resistor names, because that will be much easier. Although that, yeah, because we still need to go through every single component. We can't cheat like that, unless it's like a LED or a sensor connector where you have just a bunch of connectors connected to the same in the same way to the same chip. So we can't really do that with resistors. We have to go over every single resistor because we have to make sure that that particular resistor is supposed to be in that particular place. So what I'm going to do is going to start with R1, and that's supposed to be a 10K resistor, and then we can just skip checking the footprint and the product code. Once we have checked 10K resistor, we can assume that it's correct for other 10K resistors, but we still have to check if each 10K resistor belongs where it's placed in the schematic. So that's important. Okay, so R1. Let's see. R1 is the pull down resistor for the boot pin, which is correct because the boot pin has to be pulled high. The label, I'm going to check the label later, but I know that it's connected there and to the resistor and then to the boot pin. So all seems fine here. We just need to check that the resistor is actually a 10K resistor in a 402 package. So let's see. This is 10K resistor in a 402 package, and there's 1.7 million of them. Let's hope somebody does not buy 1.7 million of these resistors. we can go to the next then. Let's see. So I'm gonna green this one, and I'm gonna move to this one. 0, R, and 402 package. Oh yeah, and by the way, since the reset pin is, the power of the resistor is totally fine, participation, because it's not going to be leading any significant current. So next one, let's see. Next we got, let's see. So is this? Which one was it? Z0ED. Z0ED is actually not there. Okay, but we got Z0EDC, which is available, which is a new product, and which is 0 ohms and 402 package, 50 volts. Okay, so we need to update this. Let's see. Was it R10? Yeah. Let's see. So we have to update the R10 to use a different product code. Let's see. This product code is going to use EDC, and it's 402, so all good. So we can green that one. And then there is another R10 commented out, and that's because KiCad is so stupid that it doesn't realize that this comment thing is supposed to be interpreted as though it was just the R, and the numbers after the R have to be unique, but KiCad doesn't do that. So for now it's annotated like this. So R10 is designed to be in order to adjust, to be able to adjust this gain on this amplifier, and this amplifier is running at 5 volts. There is an input here, which is used for connecting normally a joystick of either a Hall sensor joystick or a potentiometer based joystick. Both work fine here, and the amplifier is basically, for the most part, it's always going to be unit gain, because all we want to do is just make sure that if a resistor based potentiometer is connected here, that we don't mess up, that we don't get different results depending on which resistance the potentiometer has. So we can connect any potentiometer based joystick with any resistance, 10K or 5K, and we're going to still get the same result on the output. That's kind of the point of this amplifier. So this resistor is in the right place. I can green it, and I can also, let's see, I can green R11 and probably R12, R13, and R14, 16, 17. $11, $12, $13, $14, $15, $16, $17. These ones are green. Next one is R100. Let's see where R100 is. Next one is R100, and I don't see the cursor again. Where is the cursor? It's like, oh, there it is. Yeah, there it is. Maybe I should be looking in the middle of the screen. But even if I look in the middle of the screen, I sometimes don't see the cursor because it's such a hiding cursor. It's so hard to see. Let's see. So this 10K resistor is designed to pull the gate of this transistor down, so that it's by default, so that it's never if there is a high Z on this input, then the transistor can never open by itself, because of, for example, because of noise or because of whatever. So I pull the gates down to 0 volts if there is, unless there is of course signal here that pulls it high. So these resistors are 100, are 103, and then 137 and 40. They are just pull down resistors. Now there is one thing that I want to check here though, because it seems that they can be connected directly, and I wonder if there is any pull down resistors built into the chip. But even if there are pull down resistors built into the chip, this acts like a good kind of like a second stage safety, because if the chip is for some reason outputting high Z here, then we can always know that the gate is going to be closed, and that's important in this case, because it can, if both gates open, then there is a short circuit here. So let's keep them there and just green light all of them one by one. So let's see, we have R100, and then they're all 10K, so let's check. So 100, 103, 137, 140. 37, 140, and then 169 and 172. And 172. So these are green, and then we can also green the second stage here. So we got 105, no, 104, 107. Let's see here. So we got 104, 107, and the next ones are 141 and 144. Let's see, 141 and 144. And the next one is 173 and 176. 173 and 176. So that's good. Then I want to let's see. Then we can just move on to the next and see what that is. Let's see. So next is oh yeah, it's the 22R resistor. So it's probably let's go over the 22R resistors as well. So the 22R resistors are there just to kind of limit the current, to make sure that we don't go over the current that the gate driver is able to provide. So when the gate here is switching, there is a gate capacitance here because it's such a large MOSFET, which has to charge in order to open this MOSFET. And the current, we want to keep the current under the rating of this chip. So that's what we do with the 22R resistor. And there is 101, 102. But we have to check, first of all, we have to check that this product code is correct, and that there is a product that corresponds to this resistor, and that product is in stock and not bought up in all entirety. Let's see. $202,000, and this is a 402 22 ohms resistor. So that's good. We can green light this one, and we can go and green light every single one of these resistors. So 101, 102, 138, 39. So that 38, 39. Where's 38, 39? Let's see, 38, 39, and 170, 171. Let's see, 170 and 171. So these are green, and then we can move on to the second here. Let's see. So this one is 105, 106. Let's see. 105, 106. This is actually going quicker than I thought. 142, 143. 142, 143. And then, like, imagine I was doing this the way KiCad wants me to do this, which is placing generic components and then assigning footprints and assigning values to these components manually. I mean, that would just be horrible. That would take me ages to do. So with my library, I can just create a component once and then duplicate it. And whenever I update any fields in the library, I can just update fields in the schematic, and all of the components, all the instances of the component are updated. So that's, to me, that's the natural way of working with a schematic. That's what I do in Altium as well. Like, that's the way to manage a component library. You create components once and then you duplicate them, instantiate them on your schematic. So let's see, 74 and 75. That's the, there we go. 74 and 75. And we can just greenlight these ones. And next is, let's see. Next is 108 and 109. Let's see which ones they are. 108. So 108 and 109. Let's take care of 108 first. But first I'm going to drink some water. Okay. So 108 is supposed to be connected to one of these pins, and we have to open the datasheet of this LAN chip, LAN 9252. I'm going to see if I can bring it up somewhere here. Let's see. LAN 9252. There's the datasheet. I'm going to close some of these. Oh, no, I just closed that one. God damn it. I have to close many of these. Let's close all of them. That's too many. Okay. Let's see. LAN 9252. And actually, I want to open the other schematic as well, so let's go to Google. And I just want to sort of get this, all of the suggestions here. It previously suggested, let's see. There was some file, what could that have been? There was this, yeah, let's look at this one. This reference schematic. This is a simpler schematic, which I closed just a few minutes ago. But I really want to see how they did it here. Let's see. So this pin is, what's the name of this pin? FXSDA, FXSDB. I think that the way they did it here is that they use those pins for I2C or something. Let's have a look here. So let's see, FXSDA. That's fiber signal detect when mode not selected. The spin function says the signal detected from external transceiver. Indicates, okay. So do we really need the resistors there? That's the question. Can we just tie them to ground? We'll leave them unconnected. Come on. What is this? Like, it won't search. Let's go manually. Let's see. No? Let's see. FXSDA. This is no. No, it's like stuck. It's totally stuck. What about reloading the page? FXSDA, come on. Come on. Yeah. Okay. Why does it jump? Because I didn't click anything. This is so weird. Like, the moment the whole dock loads, it just searches past my previous position and just goes to the like the end of file or something. What is this? Reach the end of file. Okay, let's see. This looks like it works. Okay. So this is a fiber signal detect signal, and then there is a fiber loss of signal. This pin function is loss of signal. So we're probably not going to be selecting the FX loss mode anyway. A high level indicates loss, while a low indicates valid signal. Okay. Okay. So right. So if we can tie all of them to 0 because we're not using fiber. FXSD enable. This strap input selects between FXSD and copper twisted pair mode. A level above 1 volt selects FXSD. When FX loss mode selected, the input buffer is disabled. Okay. They're latched at power on reset. Okay. So it looks to me, from this at least, that these pins can be just tied to ground without any resistors. But let's see what pin number they are on. 9 and 10. Okay. And what do we have here? Do we have any pin that is like 9 and 10? 9 and 10. 31, 32. Okay. So, are there? Where is 9 and 10? Okay, so this is FXSDB, and probably this is going to the. Let's see. Okay, right. So this is where I saw that they use the resistors, and it looks to me like. FX as the A, FX as the B. So port 0 copper, port 1 copper. But do these pins have any pull-up resistor internally then? So FX loss N. Okay. So they use these resistors, and just to avoid any problems, I think that I will use these resistors as well on this evaluation board. But on revision B, I probably may just use. I can actually even try to put some 0-ohm resistors here and see if that affects the functionality of the chip in any way. So FX loss N is also tied to 0. And then there is run LED EP size, which is tied to GPIO2. No, wait. Where is that? Was not. This is run LED. And GPIO2 is the. It must be this. Let's see. Where's GPIO2? The LED cells occupy low EEPROM size. GPIO2 is supposed to be 1 actually, because we want to use a larger EEPROM. This looks like something to actually place a note about. Okay. Let's just do a quick lookup here. So the EEPROM that I'm using here is C16. Maybe we should set this to 1 actually. Although for this schematic, this is correct. But if I change the EEPROM size, which I'm gonna have a think about, then I will have to change this trap as well. So let's see. It's good to be able to desolder this resistor and get. I wonder if there is no right. So this would be the default. So there is probably a pull-up resistor, but I don't know if there is. We can see if there is anything about pull-up resistors. No. No. Yeah. And of course we have to be searching here. Is there any pull-ups in the pin? Let's see. No. Nothing. Maybe this. Yeah. This looks like. Let's see. So requires external pull-up. Pull down and pull up resistors. Okay. Going to show them instead. Oh, cool. So this is yeah, but it doesn't say anything about pull-up resistor here. Non-variable IDC electrical specifications. So there is a pull down and a pull up. So it seems to be that there should be a pull up on these pins. Okay, anyway, the reference schematic is not using any pull up, so I'm not going to use one either. I'll just go with this and see how this works. So 108, 110, 13 and 16. Let's see, 108, 110, 13 and 16 will be green, and 109 then. 109. Yeah, that one is a bit of a question mark. Let's open the datasheet for this EEPROM. I'm pretty sure I don't need any resistor there, but I'm gonna be 100% sure. That's the plan. So let's see. Let's see. Address. It's like if anything, then the resistors should be there should be 3 resistors and not just 1 resistor. Okay, this seems to have wrapped around. So do we need to do anything about, let's see, can we see some pin out here? So where's the pin out? Also, the package needs to be okay. Let's make this one a yellow one, because I have to go back to it when I've reviewed the EEPROM itself. So So I don't want to waste time on that right now. I want to go through all of the resistors first. Let's see. This one is a feedback resistor where we let's see. So VSA1 raw, which is, let's see. So this circuit essentially adds offset to the signal, and this one creates a half voltage. But what I'm interested in actually here, I want to know what we expect here and what we expect here. So VSA1 raw is, this one is designed to be 3.3 volts at 48 volts. But we kind of multiplied like with a gain of 2, I think. What will be the gain here? Let's see. I always forget that. There is a formula. This would be inverting, and this would be non-inverting. And the gain is 1 plus R2 divided by R1. So in our case, it's R2 was which one? R2 is the feedback resistor. So this would be 5 divided by 10, which is then 0.5, and that would be 1 plus 0.5. So it would be 1.5. So that's the gain that we should be getting with this op-amp. So that will slightly amplify the signal that is coming from the voltage sensing circuit on the H bridge here. And the idea here is that this voltage is going to be amplified so that we can sense the back EMF even when the motor is spinning slowly. So it's going to be interesting to see how this works out in practice. We can green the R111 and actually R96 as well. Yeah, let's see here. We can take that one, and we can go to R88 and 89. R88 at R89, R94, 95, 94, 95, R96 and 111. And 133, 153. And R131, 132, C131, 132, and also R132, 121 and 161. So 121 and 161, and let's see, 153, we got that one, and 177, 178, and let's see, 179 and 193, 179, 193, 193, they're all 5K, 10K, that's good. And also, yeah, let's see, and we get the op-amp A, B, C, D, that's I changed in one of the previous videos. So 193, and then 1991, let's make this one green, and 1991, let's see, 97, 98, 99, all of these, and 112, 122, let's see, 112 and 122, let's see, 134, 135, and 136, 154, and 162, 180, 181, 162, 180, and 181, and 182, 194, and look at this. There are resistors missing here. Okay. So 192, 194. And we should add the resistors to this one as well. Although let me think. So this cannot go to beyond 3.3 volts. So why have a resistor there, really? There is no need to do that. Yeah, definitely. Now these ones are useless. I'm going to delete them. There is no need for any protection there because we know that this chip will never go beyond 3.3 volts. That's the supply voltage. Okay. I'm going to show the labels. That's a whole different story as well. I'll have to make a script that outputs a list of all labels, and I'll have to go through every single label, make sure that it's connected where it should be. Okay. So what's next here? We have R114. that will be these resistors. So these resistors, yeah, 114, that's the current sense resistor. So we can take that one. That's 5 milli ohms. Let's see. Can double check that it's the correct one. Right, 5 milliohms, 10 watts, and 2818 is the, let's see. So the thing is that this footprint is for a different one. So most likely this is the wrong footprint. Let's see, 2818. Yeah. And this one was 2512. Yeah. So A is 0.138 and B is 0.2. I want to see if there is anything that's like 28. There's 28, 2816, but not 2818. Right. So we could actually, what we could do is just take the 2816 and modify it. So this was. Yeah, this is definitely not right. So I'll open the resistor SMD 2816 and I'll save it as 28. Let's see. So we can just update the dimensions. 0138. This would be, that's weird. No, it's probably 3.5 millimeters. Yes, definitely. So it's 3.5 millimeters and times 5.1. So that's the size of this one, and this one is same. Oh. Okay, and then we have the distance there, which is 0.61. So we can say that these ones need to be, we should move it to 0. Let's see. Let's go like this. Like 0.3, and this one will be moved in the same way. 1, 2, 3. Kind of like that. And then we can move the silk screen as well. Great, and then this one as well. That's fine. And then this is the courtyard, so this is sort of how far away other components should go. And the way I think about it is that I reserve some space, but it's kind of like a matter of like with large components like this, it's a matter of trying it out and sort of coming up with something that is reasonable. So that when I place multiple components like this, I should be able to just line them with their courtyards and keep the same distance with them, which is also the recommended minimal distance. But with this component, it's really just arbitrary. I don't want to make it too small, and I don't want to make it too big either. So this would be custom and 2818. And what is metric? What are the metric units for this package? Let's check. There is probably some metric units here. 7146. 7146. There we go. Now, the next step is to update this one. Okay, there we go. And there's also something else that I saw here, which needs fixing. So this 100 volts just gets away. All right. And one last thing, I'll just make sure that we have the right size here. So this resist now. Okay. Let's see. Custom. That one. So just measure. I'm just gonna measure this size here. So we have width and length, and the width is 4.6, length is 7.1. And I want to see how much of it sticks out anywhere. So 7.1, right. And this one will be like 4.6. Okay. Yeah, right. So the length is also sort of the size of the package and not of this pad that comes out there and goes underneath the package. Okay, cool. So we can essentially just Greenlight, these ones. I don't think I've used the same resistance anywhere else, but there could be there are other current sense resistors, but I think I used a different resistance, slightly higher, so that it would be easier to measure using a voltmeter. Yeah, so I used 10 milliohms there, and 10 milliohms here as well. Yeah. Okay. So I can green all of the. Let's see. Let's actually go over them by designator anyway, just to get a good habit in place, because there can be, even though I'm pretty sure in this case there are only 6 of them, there could be other components where it would be dangerous to think that we should just greenlight all of the components that have the same name, because they may be used in different places. So let's just go and take 14, 150, and it's actually only 4 of them because we're only sensing in 4 phases. 14, 15, and 151. So 150 and 51. There they are. And moving on to 135K, 117. And this one is supposed to translate 48 volts to 3.3 volts. Let's double check this. So we have, let's see. So let's see, what was this now? I think it's like, could it be 10 divided by 135 plus 10? And that times 48. Yeah. So we get 3.31 volts at most here. If we're in, or actually no. So this is, we have to assume that the voltage will rise above the supply voltage. So we could get kind of, the back EMF could actually rise above supply voltage as well. So maybe it's better to use 5K there. Let's see what it will be if this resistor is, let's say, 5K. And times 60. No, 5K is too little. But if it's 10, it becomes 4.13 volts, which then gets fed to the amplifier, and so we basically end up, yeah. But this is fine in this case, because we are trying to sense. Let's see. Actually, we should have 5K here, because we're actually amplifying this signal as well. So we should have 5K here. So all of these resistors need to be changed to 5K. Yeah, that would be the best solution here, because the amplifier is going to also amplify the signal. We kind of have the option to, or actually, let me think. Yet we are not actually interested. I'm not interested in the back EMF, which is, I'm only interested about the zero crossings, right? So in this case, it's actually okay to use 10K resistor, although if the voltage rises above 3.6 volts, it's going to be triggering this diode. But the current will be very, very low because it's 135k there. Yeah, I'm gonna leave it at 10k because I'm only interested in zero crossings, so I'm not interested in the full span of this signal. And if 10k produces any issues, then I can just desolder them and replace them with 5k. So let's see. I can probably Greenlight. Let's see if 135k. This one is in stock and the correct package, and then I can Greenlight all of them. So let's see, 0402 and what? 5.1k. Okay, so this was not correct. Let's find 135k. But this is supposed to be 135k. Why does it say 5.9k? Or 5.1k for that matter? That's very, very weird. Okay. $135K1 L is 135K, but apparently like this one is also 135, but it's instead of 5.9K. That makes very little sense. 5.6K. Oh, maybe it's like 13 and 5K. Maybe this one is. Could this be? Okay. So it says. Let's see. So it says 135K is here, but in the description it says 5.1, and it actually makes sense here. It's 5K1 and 5K9. So this is wrong. In fact, this is the wrong text. And very good that I found this. I have to go to resistors, and I have to find. Let's see. I have to search for 135K specifically. And none of them are in stock, so maybe we can go to S&D resistors and search for 135K there. Let's see. Yeah, of course, 0402 as well. So never trust the product description on Mouser. Let's see. Okay, so they're not in stock. Interesting. And I thought they were, so they're not in stock. Can I use something? Let's see. And you know, if this was if this was fitted with 5K resistor, then everything would just malfunction, because there'll be larger current flowing here into the VDD303, and probably that would like break everything. So this is very important. This is an important problem to fix. But what resistors do they have then? Do they have anything that's close to 135K? Let's see what we get between 130 and 140. Actually, I could have, let's see, so let's pick this one. Let's get 120, okay. $77, 137. Yeah, it's almost that. It's pretty much that I should probably use 137, which will actually probably, let's see. So if we use 137 and we have 48 volts, yeah, then we suddenly under 3.3 volts. Which in this case is perfect. I just need to check where this resistor is used, and I just need to make sure that this is actually a 137K resistor. So 137K and 0402. Okay. So I need to. I will need to remove, I think, I'll start by doing it like this. So let's see. I'll copy this resistor first. 135K. And this will be 137K. Then like that. And then I'll also remove this field. Actually, when I'm done with this schematic, I think it would be a good idea to update all fields. Let's see. 137. And then I should just look for all of the 135K resistors. I'm gonna change these ones to 137 first. Let's see. Copy that one. That one. 137. I just don't want to open the schematic in text editor and substituting anything that's 135K to 137. I want to instead just go through every single 135K resistor and change it manually, because then I can see that my changes are not affecting anything that's not supposed to be affected by them. So 137, and then I can actually greenlight all of these. Let's see, 117, 118, let's see here, so 117, 118, these two, and 156. Uh, 156, 57. And 89, 90. And 119, 120. 119, 120. And 158, 159. 158, 159. And 192, 191. Great. And then I'm going to search for any 135K resistors. Right. Update field values. So what is this? OC adjustment. Why do I have a pull-up on it? I think I made some calculation there before that it was kind of, I didn't want to. Let's see. What was the reason I placed those resistors there? Because it should be enough to just have lower current adjustment 1 and 2. And if this one is set through a GPIO, because they are also connected to GPIOs, they should be. And if this one is set to a GPIO and pulled all the way up, then it's going to be there is going to be no limit on the current. But why did I place 135K resistors here? Okay, I'm going to change them, and I'm going to mark them yellow so I can have a look at them later. Maybe I'll just watch the video where I placed them and see what logic I had for placing them there. 178 and 79 will be yellow. 178 and 79. There. And then next 135K is just that one basically, yes. So this one goes to become 137K. Great. Then we update field values and find no 135K, which is great. And this one, the supply voltage sense, let's just review this circuit. We have 135, 137K, and we have 5K there, and there, and then this can go to essentially 60 volts. So this, having it 5K here ensures that we have a much lower voltage even when the supply rail goes above 48 volts. which is the sort of the rated voltage of this drive. So that's desirable. So we can green light R68 and R69. All right. Next on the list is R123. These ones are they're used for the Ethernet, and we can check the schematic of this. Let's see, they're 1/10 of a watt, so they should be 805. That's correct, and they're 1%. Is that 0.1%? That's strange. That should be 1%. .1%. Okay. So that's good. And 805 and according to this schematic, there should be 4 of them connected to each transmission line. So we can green light all of these and these. So 23, 25, 27, 48. Let's see, 23, 25, 27, 48. 48, really? Oh yeah, okay. So that's a 0R. 45. That's the one. And then they have 46 and yeah, they're here. So 46, 28. And 26 and 24. Right. By the way, I will also check this one. That's 0R. So we can green light 147 and 148. 147 and 148. Great. 129 then. What is 129? That's connected to the I2C bus, which has to be pulled up. And in this case, it's a 3K resistor, and it goes to SCL, SDA. The thing is, I wonder if this is actually correct, because let's see here. Was it from this schematic that I got 3K, or was it from some other place? Because this schematic uses 2K. And in fact, even using 1.2K is possible and probably better. But 3K, Let's double check that this is the right resistor as well, because this looks like it can probably be something else. this is 3K and 402. I want to search for I2C Pullup. Pullup resistor calculation. This looks good. Let's see what it says. Pullup resistor calculation. The minimum pull-up resistance. Okay. And current of output low, I guess. Okay, this needs to be, I need to make more research on this, so I have to, I'll just yellow these ones, but I know they have the right footprint and the right, yeah, and the right article number. But I need to read through the doc and determine which value they should have. So I'm going to go to R149. This one is so there was 1K going to the lab there from GPI of 2. I think this pull-up is for chip mode, so that we have chip mode 0 and chip mode 1 in low. Close that one and let's check chip mode. So 0, 0 means that port 0 and 1 are connected to internal PHYs A and B. Which looks like what we need, and which means that right, okay. So it's quite possible even that this would actually be low by default if the LED is connected there. So R149 and R160 needs to be reviewed again, because I need to simulate that. Let's see. R152. I'm going to try to greenlight as many as I can right now, and then I'll go back and handle those question marks a bit later. So let's see, R152 and 155, these ones are, yeah, we can greenlight these ones because they are 270R and they're necessary for the diode anyway. So we can make these ones green. And 163 is the next one. R163. Right. And this goes for this resistor divider that goes from the HAL sensor into the HAL inputs. And the whole point here is to, let's see, we want to drop the voltage from 5 volts to, this will be 10k and this will be 5k, to 3.3 volts. And in this case, this is actually wrong. Okay, this has to be the other way around, I think, because we need to have 5k there and 10k there. Yeah. And just to double check this, let's go to so we have R1, so we have always R2 divided by let's see, so R2 is 5k in our current configuration, and R2 would be divided by the sum of R1 and R2, which means in this case that if we have a source voltage of 5 volts and we have R1 equal to, in this case then 10k, and yeah, it doesn't matter if it's ohm or kilo ohms, it will still give the same result. Then we have 1.66 volts, but we have to move the 5k to the R1 position, and then we get 3.33 volts, which is very good that I've noticed this. I'm gonna move them around, and I'll just do like this. Let's see, move and rotate. And move, rotate. And then this one will go there. And then this one there, and this one there, and this one, rotate that one like that, and this one there. So 183, 84, 85, 83, 84, 85, and 163, 67, and 65. 63, 67, and 65. And also, I'll just double check that this is, yeah, this should be 5k, but I have to double check it as well. Let's see. 5k 0402. Great. Yeah, and then we have the other one up there as well, I think. Or is it down there? Yeah, down there. So I'm gonna move these ones as well. So 86, 87, and 88. And then 86 move there, and 87 can move there, and 88 can move there. and let's see, 64 can move there, 66 can move there, and 68 can move there. Now we can just move these ones up there. Okay, 64, 66, 68, and 86, 87, 88. 64, 66, 68, and 86, 87, 88. And R18 is the next one. R18. This one is okay. So the point of this circuit now is to divide the voltage output of this amplifier and to feed the ADC. And for feeding the ADC, these resistors have to be very small, but not too small so that we don't waste current by having a resistor divider that is basically shorting the output to 0. But instead, I use 1.5K and 3K there. So what I get is, let's see, so we have R2 is 3K and R1 is 1.5 and 3K, and we get 3.33 volts on the output here as the maximum value, which let's see, what if we use 5K though? Because I'm just thinking that right, it's going to be 3.33 volts, but then the output of the amplifier is actually not 5 volts. It's probably like let's say it's 4.8 volts. Then we get 3.2. So this is perfectly fine. All I have to do is check that both 3K and 1.5K. I think I checked the 3K, so I only need to check 1.5K. R18 is that one, 1K5. So that looks, based on the article number, this looks correct. But I'm just going to search for this article number and check. Zero 402, 1.5K. So this one can be green lighted, and we have the 3K. Did I green light the 3K? Okay. I'm going to check this. So R26. This looks like a 3K resistor. Zero 402 3K. Great. So I can green light R26, and then I can just move down here because I have 8 of them, and I can green light R19, R27, and R20, R28, and 21, 29, and 22, 30, and then let's see, so 23, 31, 23, 31, and 24, 32, and 25, 33. 24, 32, 33, 25. There we go. So a lot of resistors, all greened at the same time. But then I have also the 1.5K or 10K here. Let's see. So we can green them as well, all at the same time here. I think actually I've greened them already, because, or have I? Okay, so it starts at R2. Okay, I remember I greened R1, but not R2. So R2, 3, 4, 5, 6, and 7 and 8. Let's see, 2, 3, 4, 5, 6, 7, and 8. So green lighting all of them, and I can also go ahead and just green light the R10 here as well. Let's see. I think R10 is probably already green. Yeah. Right. So let's see. Is there anything else here? D1, D2, D3. I guess we'll just yeah, we already green lighted those. So let's move on to R195. Yeah, that's green because that's designed for that diode there, let's see, I can green light that one as well. And then there is 196. Which one was that? 96 and 97. So 96 and 97 is supposed to be 10K. We got 35K. So I think I changed them to 10K. But I did not update this list, so that makes sense. I remember I simulated that. So 98 and 99 for the next. 98 and 99. Yeah, this one is for the R200, which we are going to, let's see, 470R. Yeah, 99 can be green, but I'm also gonna check this R200 because I want to make sure that I have a number that specifies the resistance of that at 25 degrees Celsius. So I need to, let's see, I'm going to do like this. I need to open the data sheet and I'm going to check R200. I'm also going to go here. I think it's a 10K. It looks like it's a 10K because it says 103 there. So never trust the description. I'll go directly to this resistor, and we have 10K, 1%, 0.402, I think. Yeah, 0.402. So this one is this one is 10K. So I'm just gonna add some text to it that says that it's 10K. Let's see. Okay. Let's make this 10K. Okay, so I can green light R200 as well. so next one, R201. R201. Oh yeah, so that was the 10K. Let's see. Okay. And wait a minute, so right, there are two of them. Okay, I see. So there was one R200 first, which was there. This is one of the drives, and then there was R201, which was on the second one. So here we got R201 and R202. And we can greenlight all of them like that. So yeah, this is going well. R34. Is R34. These ones are for the address. So the idea here is to be able to kind of like set the address with resistors, but I don't think this is the correct way to do it. So I'm gonna check the data sheet of this chip. But I will actually make them yellow 34, 35, 36 for now. And I may remove them actually later, but we'll see. For now they can be yellow so that I can go back to them later. 37. Let's see. R37. This one is, let's see. This one is just to have a 15K resistance between the comp pin and this capacitor here. So I think since this schematic is taken from the Texas Instruments site, I think that we trust it for now, and then I'll evaluate it and I'll see if there is any problems with this schematic. But I'll greenlight those resistors for now, because I know they have the right package, and I know that I know why I placed two resistors there, so that I can just make them green and then go to R39, which is there, and this one I have to check I have to check and make sure that the package is correct. So let's see. So this one is 805, 10 milliohms, 805. So basically, this is easy to double check. This is an 805 and yeah, 10 milliohms. So R39 is fine. Can greenlight that one. And then there is R40. It's 1 mega ohm. Yeah. Let's see what we have here. One mega ohm, 402. Yeah, can greenlight that one as well. 41 and 42. Where are 41 and 42? R41. This one is here. Okay. So this is analog output, and this one is using let's see. This one is using 5 volt output, so the gain is set to 1.5, and the chip here outputs 3.3 volt on the output. we can Greenlight 41, 46, and I'm just going to compare this to the schematic that I have here. Let's see. Yeah. Okay. So I can just go through all of these resistors here and Greenlight all of them. 41, 46, 53, 56. 41, 46, 53, 56. And then 42, 47, 54, 57. 42, 47, 54, 57. So that's fine. And then 43. Let's see. Where is 43? Right, that's the same thing here for the addresses. So 43, 45, and 44 are going to be yellow. '48 and '49. Let me minimize this one. There we go. R48. R48, 49. I need to check on both of them that this is the right component, but I'm not going to check the functionality until I get to this chip. So I just check to see if this is the right component, to see if it's what it says that it is. So 47 is this one. It looks by the product code that this is 147 K resistor. Let's see. 147. And for some reason I'm not getting any suggestions anymore. So 147, and it's a 603, but maybe it's required to have a 603 here. Although it won't seem to me that it is. So was this a mistake? Let's see, 147, 603. What about this one? No, I think this was somewhere in the datasheet for the chip that they were supposed to be 603. So I used 603. $10.5K, and what's this? Yeah, this is 603 as well. And since my document here says that they're supposed to be 603, I'll greenlight them. But if I realize that they can be 402, then I may change them. But for now, I think it's fine. So 470 R50, right? R50. R50 is here. Yep, we can greenlight that one. And 51. These are 22R, and they are the same as used over here, so it's 22R. Now, something that I need to check here though. So 22R here is probably fine, but 22R on the MOSFET, it could actually be that the power dissipation would be too high. So maybe those resistors need to be 603 and not 402. in which case I would just update all of them and use 603 resistors instead. But I think actually that's an important consideration here, because there will be a lot of current flowing through these resistors. We could say that it's like 2 amps. No, let's say that this is okay. So this will go perhaps up to this will go to like 65 volts maybe. So above 48 volts, which means that we have a current of let's see. Let's make sure that it's like, let's say it's 60 volts. So 48, and it's probably like 12 volts in the charge pump. So let's say 60 volts, and divided by 22. So we get 2.772 amps. That would be the maximum current through this resistor. And that's not something that I think a 402 part can handle. So I have to go back to these resistors, and I have to change them, I think, or completely remove them actually. I think most likely I will remove them completely, because not even the reference schematic has those resistors. So this is going to be removed, I think. I have to check that. Let's see, R55. What about R55? R55 is that one. Yeah, we can just say okay on that one. And actually, I think I'll stop here, and I'll do some research on the resistors, because I have to make sure that I have to find out if I need to remove those resistors from the schematic from the MOSFETs, or if I can perhaps maybe change the package. So yeah, I'll stop this video here and continue in the next video. I probably need to go out with my dog now, because she's really she really needs to go out now. Yeah, okay.